Welcome. This is the first module in a series of lectures that I've posted on my website. These lectures are going to deal with the question, how do we identify glaucomatous damage on OCT scans? And before we start the first one, I encourage you to listen to the brief introductory module that provides some background as well as updates. So in this first module, I want to supply some background material about the OCT. And this information is familiar to, some of it will be familiar to some of you. Maybe even a few of you will know nearly all of the information. I encourage all of you, however, to listen to this introductory lecture. It's not very long, and it will supply a common set of concepts and definitions that we'll use in the subsequent lectures. So before I begin, there's the obligatory financial disclosures. I have grants and also equipment from both Topcon and Heidelberg Engineering. All right, so let's start with a brief review of retinal anatomy and glaucomatous damage. Okay, retinal anatomy. So this little black line here is meant to indicate the retina. It's about 300 microns thick. And to the right here, indicated by this red arrow, is an electromicrograph of human tissue. And you can see the three layers of cells. The cell bodies are the rods and cones. The cell bodies here are the bipolars, but also horizontal and American cells. The cell bodies are the ganglion cells. Light comes in this direction. It's absorbed in the outer segment of the receptors. And then the electrochemical activity flows towards the brain. Receptors synapse with the bipolars. Bipolars make synaptic connections with the ganglion cells. And the axons of the ganglion cells leave the eye as the optic nerve. And over here, I indicate that. And you've got about 1 million ganglion cells and 1 million axons in the optic nerve. Receptors in a nuclear layer, we're agreeing on terms here, in a plexiform layer, the retinal ganglion cell layer, and then the retinal nerve fiber layer that contains the axons of the ganglion cells, but it also contains blood vessels and glial cells. Excuse me. Now, since glaucoma kills retinal ganglion cells and their axons, glaucoma is going to affect the plexiform layer, where the dendrites of the ganglion cells are. It's going to affect the retinal ganglion cell layer, and it's going to affect the retinal nerve fiber layer. These are the layers damaged by glaucoma. All right. Second, let's review a little bit about OCT scanning and what glaucoma does and how it appears. So you probably know that you can think of OCT as ultrasound, but with light. And just like you can pick up a small lump in the breast with ultrasound because of the way the sound is reflected, you can pick up small structures in the retina because of the way light is scattered or reflected. Because light has a shorter wavelength, the resolution of the OCT is far better than ultrasound, and it's of the order of 5 to 10 microns. All right, here's a line scan on the right here through my fovea. It's about that much of my back of my eye, and on this schematic here would represent about that much of the eye. Here is, I usually point out this is not me. This is post-mortem histology of human tissue. If it were eye and you scaled it up to fit in my eye, it would look something like that. So we can blow up this region and compare the histology to the OCT. So on the top we have the OCT, on the bottom we have the histology. So first of all, take a look at the retinal nerve fiber layer here. It's made up of X, and here it is down here in histology, and Here it is on the electron micrograph. It's made up of axons from individual cells. I show an example of one axon. Notice it's going to be very thin here because you have got very few ganglion cells. It's going to get thicker and thicker as you recruit more and more axons from the increased density of ganglion cells. And that would be an example of an axon. All right, then the retinal ganglion cell plus in a plexiform layer, we're going to lump that together. You can see, or you can usually or often see the distinction on OCT, although it might be difficult, especially in some patients. So we're going to lump them together, and whenever I say retinal ganglion cell in this talk, I'm going to mean retinal ganglion cell plus in a plexiform layer. You can see on histology, because it's a different technology we're talking about in the case of histology here, structures that absorb the dye differentially or the stain, whereas in the OCT we see structures that reflect or scatter light differently. So retinal ganglion cell plus in a plexiform layer. All right, so since glaucoma, kills retinal ganglion cells and their axons, which layers are going to be affected? I'll give you a moment to think about this yourselves. I want this to be interactive. Studies have shown you learn better that way. So if this would be a ganglion cell, that would be about the ganglion cell layer location, and then your axons like this. So you're going to expect this layer to be affected, the retinal ganglion cell plus in a plexiform layer, and you're going to expect the retinal nerve fiber layer to be affected. So both of those are affected. All right, so the other piece of anatomy you need to keep in mind is the route that the axons, sometimes called nerve fibers, travel as they go to the from the cell bodies to the disc. And they travel in bundles. And this is meant, this schematic you see in lots of review articles is meant to capture the following fact. The ganglion cells here on the nasal side of the fovea send their axons more or less straight in, whereas the ganglion cells on the temporal side of the fovea arc around and avoid the fovea. They bunch up here in the inferior quadrant because they're now meeting up with axons that are coming from wide areas of the eye. Remember, this is only one small portion of the eye. And this is a region that's particularly vulnerable to damage from glaucoma. Same thing's happening up here. I didn't draw in all the bundles, but it's the same pattern. Okay, because of this particular aspect of the anatomy, and because glaucoma acts at and in the disc itself, local defects here will produce these characteristic arcuate forms. All right, third item I want to review is visual fields. And again, I'm assuming that most of you, if not all of you, are familiar with visual fields. So it's often said that there's no litmus test for glaucoma, meaning that there's no single test you can do that will confirm glaucoma. No blood test, no single test. So glaucoma is often described as a progressive optic neuropathy, meaning a disease of the optic nerve, that's characterized by a specific pattern of anatomical and behavioral changes. And historically, the anatomical changes were identified by looking at the disc, looking at it either with direct examination or with photos, sometimes stereo photos. Now, increasingly, OCT scans are being used as well. For behavioral changes, the standard technique has been the visual field, so-called static automated perimetry, at least for the last, 30 years or so. All right, so here's a very popular machine for static automated perimetry. I want to review this report, which is called the 24-2 report. There's a slightly larger version, the 30-2, that some of you probably use. Now again, I'm assuming basically you've been through this material, but I just want to review a few things that we're going to be using so that you want to keep in mind. So the individual here is asked to identify and press a button whenever he or she sees a spot of light which is relatively small and relatively brief. Now the spacing of these test spots is rather gross or crude, or in the sense that these tests, here it shows you the location of the test spots, they are spaced every 6 degrees, starting up and over by 3 degrees from fixation. These numbers here, which are called total deviations, right, are read in the following way. They're dB, meaning tenths of a log unit. A little confusing, but I will make it very simple. Minus 13 dB is really 1.3 log units less sensitive than age-matched control group at this point. That is, in other words, if you take the anti-log, this individual that had this minus 13 at this point needed 20 times more light, that is, was 1/20th as sensitive as age-matched controls. Excuse me. Even more so, we'll be making use of this plot, of these two plots here at the bottom, which are probability plots, either for total deviation or for pattern deviation. And the way you read it is shown off to the right here. A small spot means not significantly different. A symbol with these 4 dots means significant at the 5% level, and then graded up to significant at the 0.5% level, depending on the symbol. One of the statistics here that we'll make use of is mean deviation. It's not quite this, but it can be thought of as the average of these values. This is the most common visual test used to diagnose glaucoma. Thousands of these are done every day. Now, a common set of criteria used for defining abnormality, and this is criteria that was used in the Oates trial, it is said to be abnormal if either the pattern standard deviation or the glaucoma hemifield test is abnormal. So this is glaucoma hemifield test, and then this is the pattern standard deviation. And you can see in this case, pattern standard deviation was significant at the 0.5% level, and the glaucoma hemifield test was outside normal limits. All right, so for some purposes, and we're going to talk a lot about this in the future lectures, you want a finer look at the macula, and in that case we use the 10-2, which is spaced, the test points here are spaced every 2 degrees, starting up and over by 1 degree. And again, there's pattern standard deviation and mean deviation. In this case, the pattern deviation was normal, the mean deviation was abnormal. All right, just to put this in perspective, let's go back to our fundus view and put these 10-2 points on top. You'll notice that they've been morphed, right? You can see the spacing here is not equal, even though the spacing to the left here is equal. This is superior retina, inferior visual field. This is inferior retina, superior visual field, because remember, the retinal image is flipped, right? Flipped up and down, but not left, right. Okay, so, 10-2 points, and this is what the 24-2 points look like. Now, we're going to be talking a lot about the influence of glaucoma on the macula. And macula actually is defined in different ways by different scientists. The anatomist has one definition. The clinician often means the area within the arcade here. I'm going to be using the typical definition used by physiologists, and I'm going to define the macula as plus or minus 8 degrees So here's a circle I just added now with a radius of 8 degrees. Within this circle, you have less than 2% of the total retinal area, because remember, the retina is much larger than what you're seeing here. But in that area, you've got over 30% of the retinal ganglion cells. Right. So here's what the macula looks like on the 10-2. You can see all the points that are within the macula. And on the other hand, if you look at the 24-2 here, there are only 4 points. And I'll say more about this later. Here's a pseudo-color map of the thickness of the retinal ganglion cell layer. And dark red here is very thick. Dark blue is very thin. And you can see this donut here of very dense ganglion cells that are so important for face recognition, driving, reading, all these everyday activities. If we look at a OCT line scan through the center, it looks something like this. And you can see the ganglion cells here being pushed aside. I'll say more about the why they're morphed in a little bit later, but essentially it's meant to take into consideration the fact that these ganglion cells are pushed aside. All right. Fourth, I want to say a little bit about the original OCT circle scan report. And the reason for this is to understand what we are doing in the present. We need to understand the past. Now, this is true in lots of walks of life, but it's particularly true here when it comes to understanding the current practices used to identify glaucoma with OCT. All right, so 10, 12 years ago, there was only one machine. It was the Zeiss time domain machine, and we all looked at one report, a single report. This is the report we looked at. That report was based upon a circle scan that was an average of a number of scans. So the machine, one thing you should know about OCT is you only have 2 seconds or so to obtain a scan before the eye movements start messing up the quality. This machine was very slow, so the best it could do was to use its 2-3 seconds to obtain an average circle around the disc. Again, so you want to understand this report to understand why we're doing what we're doing in the clinic at the moment. All right, so let's take a look at the circle scan. This is where it's obtained. If you blow it up, that's what it looked like. The resolution was terrible. You would not know by looking at this image how well this technology was doing. Because I think it's safe to say that this technology has changed the face of glaucoma. This is pseudo-color, where red means more intense. All right, now, what the computer did then and does now is draws a line through the boundaries of the retinal nerve fiber layers. So the upper white line here is the vitreal retinal boundary, and the second white line below it is the boundary between the retinal nerve fiber layer and the retinal ganglion cells. This process by which these boundaries are found is called segmentation. So the distance between these two white lines is the thickness of the retinal nerve fiber layer, right? That's a retinal nerve fiber layer. The distance is the thickness, and that's what's plotted here in this black line. So this black line on this plot is the thickness of the retinal nerve fiber layer derived from that image. This is sometimes called the retinal nerve fiber layer profile. It's sometimes called a T-SNP curve, because the scan went from temporal, that's the T, to superior S, to nasal N, to inferior I, back to temporal T, T-SNP. Green here is the 5 to 95% confidence interval, so this particular eye is falling within that interval. 1% would be the 1% confidence interval, and yellow would be 5%. Okay, so why this bumpy shape here with the peaks and the troughs and so on? Well, to understand that, let's go back to our surface anatomy. And the thin place right here, the beginning of the middle of the temporal quadrant, is thin because the axons here are going more or less straight in. This peak here, shown in red, it corresponds to those axons bunching up in the superior part of the disc. When we get to the nasal, axons go straight in again. So it's thin, and then this part's thick again for the same reason, right? This is the retinal nerve fiber layer profile. This is sometimes called the T-snake curve. So the thickness here can be thought in terms to represent the number of axons, but it's more than just axons because the thickness is also influenced by blood vessels and glial cells. All right, now with the newest scans, and by newest scans I mean for the last at least 8 years, this is what we can now see. Look at the beautiful detail, right? Images are much better than the original scan. That was the original scan, right? Who wants to look at that? This is a thing of beauty. You can not only see the retinal nerve fiber layer and fine structure, we can see the rest of the retina as well. Again, this is in pseudo-color. Retinal nerve fiber layer, retinal ganglion cell layer. All right, now, because these machines are faster, you have a choice. You can use your 2 or 3 seconds to get a high-resolution circle scan, or you can use that time to get multiple line scans, called B scans, and produce a cube scan. Cube scan, volume scan, 3D scan, these are different terms for the same thing. So, in this particular case here, there are 128 scans obtained within a few seconds. Each one looks something like this on the right here. That's the retinal nerve fiber layer. This is a pseudo-color thickness plot now of this entire region. And again, red is thick and dark blue is thin. You can derive a circle scan from this, right? And that's what the derived circle scan looks like. So this is retinal nerve fiber layer thickness. So you can just, instead of scanning this circle, you have a lot of extra information, and you can get the information around the disc as well with this derived circle scan. Right? So there are 2 ways to get circumpapillary retinal nerve fiber layer thickness. You can obtain a circle scan, you can get a disc scan, a cube scan, and then derive it. The circle scan has the advantage that you can see better details. It's higher resolution. It's got the disadvantage that if the tech doesn't center it on the disc, you can't do anything about that afterwards. The cube scan, the resolution isn't quite as good here, but it's not bad. But it's got the advantage that you can now derive this circle scan afterwards, so you can adjust, or the software can adjust where the center of the disc is. Right? So they both have a use. Final point I want to make in this module, that we're living in the past. Now, what do I mean by we're living in the past? Well, again, let me go back to this. 10 years ago, 1 machine, 1 report, right? Based on this simple circle scan. Those of us who made use of this at that point learned to look at the summary statistics. That is, we looked at these pie charts, which was the thickness by clock hour, or retinal nerve fiber thickness by quadrant, which is even more popular. We looked at the average thickness here. We didn't look at the scan. Who would want to look at the scan anyway? Resolution is so terrible. Right? We didn't look at that. Many of us did look at the actual thickness, right? That's based upon that. All right, so here are some of the reports from the recent reports from various manufacturers. There's a recent report from Zeiss, right? Notice we're still featuring the summary statistics, right? Quadrants and average thickness. There's this information here, which is new. Some use it, some don't, right? It's turned into probability plot in this case. And here is the reports from two other manufacturers, or two other manufacturers. The point I want to make here is clinicians still depend largely on these summary statistics, quadrant thickness, overall thickness. And I'm going to tell you later that these metrics have been shown to be suboptimal. What they should be doing is looking at images. Some of these reports don't even have the image on it. This is a beautiful technology with beautiful images. And if they do have the images, they're often very small. Of what use is that image, I ask you, or that one? Right? So I'm going to argue we're living in the past. We're still doing things as if we had the old time domain machine. We're looking at metrics instead of looking at images, and we're making use of these pie charts instead of looking at not only the image, but I'm going to try to convince you later looking at thickness and probability maps, and more about that in subsequent lectures. Thank you. Just a little bit of review. I have a couple of review slides here. So which layers are affected by glaucoma? Well, in a plexiform layer, retinal ganglion cell, retinal nerve fiber layer. Right? Where are these layers on the OCT? All right, so there's a line. This is a scan through the center of the fovea. A ganglion cell would sit about like that. So it's this layer that we're interested in, retinal ganglion cell layer and retinal nerve fiber layer. They're affected by glaucoma. Where are they on the horizontal scan? Here's one of the 128 line scans through the disc. That's the retinal nerve fiber layer. That's the retinal ganglion cell layer. And then finally, where are they on the OCT circumpapillary circle scan? That's the retinal nerve fiber layer. And there are two ways of obtaining this circumpapillary retinal nerve fiber layer thickness plot. You can get it with a circle scan, or you can derive it from the cube scan. Thank you, and please proceed to module number 2.